This is our first example of two, and it's of the more intermediate range with regard to difficulty. Let's tackle it right away. Here is example one. This says a spherical balloon is inflated so that its volume is increasing at a rate of 3 cubic feet per minute. The question here is, how fast is the diameter of the balloon increasing when the radius is 1 foot? At that moment in time when the radius is 1 foot, so the big picture here, you guys, if you picture yourself blowing up a balloon, you know, at the very beginning of blowing up a balloon, that thing increases in size very fast. And then toward the end of blowing up the balloon, it's getting bigger, but in smaller and smaller increments. So we want to know, in that moment in time, when the radius is 1 foot, how fast is the diameter of the balloon increasing? And this is how the idea of related rates can help us solve such a question. So we use this acronym called DREDS, D-R-E-D-S, to help us remember the steps to take when solving these problems, because they're quite complex. And if you do the steps in this order, it'll help you get home. We found that DREDS is really helpful to track things. So the D there stands for diagram, make a diagram of the situation. The R stands for record the related rates that they give you in the problem. The E stands for you got to come up with an equation representing the problem. The D then take the derivative of said equation and do so implicitly. And lastly, substitute and solve is the S. So that's the way the clock ticks here. First, we're going to make a diagram. D for diagram, right? Well, here's that balloon with a diameter. Well, the diameter's got a formula. It's equal to 2 times the radius. Why didn't you put 1 foot in there yet? Okay, so this is an important point of emphasis. You know, the radius and the diameter, they're going to be changing throughout this scenario. So any dimension that's going to be changing throughout the scenario, we don't want to put that in until later in the problem. Anything that's concrete, not changing, we can put in the picture right away and in the equation right away. More to come. Anyways, we're now going to record the related rates. Well, these are rates like, think of miles per hour. This is a rate. In this problem, we're given the volume is increasing at 3 cubic feet per minute. So we call that dV dt. The derivative of volume with respect to time is equal to 3. And dd dt is the derivative of the diameter with respect to time. That's what we're asked to find. So we have recorded the related rates. That's all that R is standing for. Now we need to come up with an equation. Well, it's got to be pretty obvious here what the equation is. Sometimes we've got to hunt deeply for this equation. Sometimes it's very apparent what equation we have to use. In this case, we're talking about the volume of a sphere. And typically in calculus, you guys, the volume formulas are given to you, but anything like Pythagorean theorem related or area related, those are things you needed to know by heart. But this volume of a sphere formula is 4/3 pi r cubed. And I'm going to write this in terms of d diameter. So I'm going to replace that r. If you take the diameter and cut it in half, you get the radius, right? So now we've got this equation written in terms of d. And that's going to help us, because in the end we're asked for that dd dt. We want to make sure our equation is written in terms of d. All right, so let's take that d over 2 and cube it. Well, that's d over 2 times d over 2 times d over 2. That's going to give us a d cubed over 8. D cubed over 8. And if you take those two fractions and go top times top, bottom times bottom, you see how you're going to get 4 over 24 pi d cubed. Reduce the fraction. 4 over 24 is 1/6 in most countries. And now I've got an equation. So I've got 3 steps done. I've drawn a diagram. I've recorded the related rates. And I have an equation ready to go. I now have to take the derivative of this equation. And I need to do so implicitly. So we're going to catch up here. So this next step in DREDS, we're going to take the derivative of this final equation we've come up with, and we got to take the derivative implicitly. So if I were to take the derivative of this thing, 1/6 pi is a constant that I can use as a factored out multiplier. And then I'm going to take implicitly the derivative of d cubed. Well, d cubed has derivative 3d squared times dt. You learned about how to implicitly differentiate 2 days ago. Moreover, you know, at the very beginning when we have that v, we actually differentiated that. We got 1 times dv dt, implicit differentiation there as well. So some students missed the boat on that. Both variables that we have were implicitly differentiated. So now we have this scenario, and we're going to simplify our world a little bit. You see the constant 3 multiplied by the fraction 1/6 gives us 3/6 or 1/2. That's all that happened there. Okay? And we have differentiated that guy successfully. It's now time to substitute and solve. So back in the original problem, it told us that it wanted to know what was going on with the change in the diameter. What was the rate the diameter was increasing? At the moment in time, the radius was 1. And remember, we have a dv dt equal to 3. So when we substitute and solve, dv dt I know is equal to 3 equals 1/2 pi. The diameter, again, it told us the radius was 1, so I know full well the diameter is equal to 2. And then the derivative of diameter with respect to time is the only thing missing here in this equation. And so we got to isolate that and solve for it using our Algebra 1 skills. Welcome to Algebra 1. So we have 3 equals 2 pi dt. Let's see. Please excuse my dear Aunt Shaniqua. Says you got to do the exponents first. 2 squared is 4. Half of 4 is 2. That's how we arrived at that, 2 pi. Now divide both sides by 2 pi. The 2 pi's cancel on the right. You're going to get dt equals, when you use your calculator on that, remember to use parentheses on the bottom, 0.477. Now, a lot of people get a numerical value. They have no idea what that means, so you got to finish the job here. You do so by writing what we call an ATM statement. By the way, we substitute and solve that. Gets a question, check mark there for our last step. So this is called an ATM statement. ATM means at the moment. At the moment. At the moment the balloon's radius is 1 foot, its diameter is increasing at a rate of 0.477 feet per minute. That's how you do a related rate problem. So you'll get used to these. I know it looks absolutely impossible at first glance. You'll see another example and start to pick up a fraction of it. Then you'll work with your teacher and have a little more, then go solo and start piecing this puzzle together. So there is some exposure to a related rates problem, example 1. Example 2 on the way. Over and out.